In this presentation, I am going to explain the previous GATE questions and answers for the year 2022, and the topic covered is electrical machines. Now let us see the first question, 2022 GATE question that carries 1 mark. The frequencies of the stator and rotor currents flowing in a 3-phase 8-pole induction motor are 40 Hz and 1 Hz respectively. The motor speed in RPM is to be calculated, that is round off to nearest integer. Therefore, the rotor current and stator current frequencies are given. Rotor current frequency is 1 Hz and the stator current frequency is 40 Hz. Now, what is the speed of the rotor? That is the question. That is, the rotor current frequency is given as 1 Hz and stator current frequency is given as 40 Hz. And the number of poles of the induction motor 8. And the relation between the stator and rotor frequency is, the basic relation is that rotor frequency is equal to slip times the stator frequency. The rotor frequency is equal to slip times the stator frequency, or slip equal to, we can see that one, it is equal to the rotor frequency divided by the stator frequency, or stator current frequency same as the supply frequency. Therefore, that is given as 40 Hz here. Therefore, the slip of the motor is given by, that is the frequency of the rotor current Fr divided by the frequency of the stator current, which is equal to 1 by frequency 1 by 40, which is equal to 0.025. Therefore, the slip of the motor is given by 0.025, or that's equal to 2.5%. Now, the slip of the motor definition is that it is equal to ns minus n divided by ns. And from this equation, we can find out what is the rotor speed, n equal to ns into 1 minus s. Now, we know the s is calculated and ns is to be calculated. That is, synchronous speed is given by 120 f into p, where 1 f is the supply frequency, is nothing but it is the stator current frequency, which is equal to 40 Hz. Therefore, it is equal to 120 into 40 divided by number of poles 8, which is equal to 600 RPM. Therefore, this is the synchronous speed, and that is this one, ns. You have to find out what is the speed of the rotor, n, which is equal to ns into 1 minus s. S is already calculated as 0.025. Substituting that value of the s as the ns in the equation, we can get the rotor speed, or the motor speed is given by 600 into 1 minus 0.025, or that's equal to 585 RPM. The rotor speed is given by, or the motor speed is given by 585 RPM. Now let us see another problem, 2022 GATE question, and that carry 2 marks. A 280 volt separately excited DC motor with armature resistance of 1 ohm, armature resistance of this one equal to 1 ohm, and constant field excitation, that is the field excitation is constant, drives a load. The load torque is proportional to the speed. The motor draws a current of 30 amperes. The motor draws a current of 30 amperes. That is armature current equal to 30 amperes. When running at a 1000 RPM. When the motor is running at 1000 RPM, it draws a current of 30 amperes. Neglect the frictional loss in the motor. The speed in RPM at which the motor will run if an additional resistance of 10 ohm is connected in series with the armature. That is the speed of the motor when a rotor, series to the rotor or series to this armature, we are connecting another resistance of 10 ohm. Then what is the corresponding speed? That is the question. Say separately excited DC motor. And separately excited DC motor. And the terminal voltage, supply voltage is given as 280 volts. And the armature current at 1000 RPM, it is given by 30 amperes. And the armature resistance is given as 1 ohm. And the speed at which it is running at 30, or that is, when it is driving a 30 ampere current, that is equal to 1000 RPM. That is, we are taking N1 as 1000 RPM and the corresponding current IA1 as 30 amperes and RA equal to 1 ohm. And the corresponding back EMF, the relation back EMF when it is running at 1000 RPM, EB1, I'm telling that the first case that N1 equal to 1000 RPM. EB1 is given by VA, that is armature voltage 280 minus IA1 into RA. IA1 equal to 30 amperes into the RA into 1 ohm, which is equal to 250 volts. Therefore, the back EMF EB1 corresponding to the speed 1000 RPM is given by 250 volt. Next one, again the back EMF definition, as we know that it is equal to 5Zn divided by 60 into P by A. That is the relation of back EMF. Or we can say that one, all other parameters are, because phi is a constant, say separately excited with a constant excitation. Phi is constant, all Z constant, P is constant, number of parallel paths A is constant. Then we can write it as EB equal to a constant into N, or EB can be proportional to the speed. That the back EMF is proportional to the speed N, or that is we can write it as, in this case, EB1 corresponding to 1000 RPM. EB1 is proportional to the speed N1, which is equal to 1000 RPM. Therefore, EB1 is proportional to N1. That's the question. That is the equation 1. Next one, the relation of the DC motor, the torque and flux and armature current is related by torque is proportional to phi into Ia, or in this case, I am taking Ia1. Therefore, torque phi is a constant, or we can say that one torque corresponding to the first case, that is when is running at 1000 RPM, that the first case torque T1 is proportional to, of course, phi into Ia, or that's proportional to Ia1. We can say the Ia1. Again, here torque is, it is the problem, it is given that torque is proportional to the speed, that is given in the problem. T1 is proportional to N1. For taking these two equations, we can write it as N1 is proportional to Ia1, because if I is a constant, N1 is proportional to Ia1. Therefore, we are getting two equations. N1, the speed is proportional to the armature current. For N1, that is the first case 1000 RPM, that is proportional to the corresponding current Ia1, which is equal to 30 ampere. Therefore, this is a third equation. We'll be seeing the later in the coming slide. The question is that when an additional resistance of 10 ohm is connected here, what is the speed? That is the question. For when additional resistance of 10 ohm is connected in series to the armature, that let us see that, or take it as the speed as N2. We are assuming that that speed equal to N2. Or as we already seen that speed N is proportional to the armature current. And in that way, we found out N1 is proportional to Ia1. Here, the second case, when 10 ohm is added in series to the armature, corresponding speed N2 can be proportional to Ia2. Therefore, if you consider that the third equation, which is already we are written N1 equal to proportional to Ia1, and here N2 is proportional to Ia2, or if you take the ratio here, N2 by N1 is equal to Ia2 by Ia1. Or we can say that the current in the second case, when a 10 ohm resistance is connected, the corresponding armature current can be calculated Ia2 equal to Ia1 into N2 by N1. N1 is means initial, in first case, what is the speed? 1000 RPM. Therefore, it is equal to 30 by 1000 into N2, or 0.03 N2. Therefore, the second case, the armature current can be written as 0.03 N2. Now, again, our aim is to find out the speed N2 when 10 ohm is connected. Therefore, in that one, we have the relation already. We have seen that EB2 is proportional to N2, or EB1 is proportional, or EB2 by EB1 equal to N2 by N1. Or N2 by N1 means N2 by 1000. That is equal to EB2 by EB1. Or EB2 is given by the supply voltage is 280. That is the 280 minus the drop across this resistance. That is Ia2 into the armature resistance Ra plus the whatever the resistance we are connecting series. That is an ohm resistance. R external, or that is divided by, what is that? Of course, that divided by the corresponding that is N2 by N1, which is equal to EB2 by EB1. EB1 is already we calculated, is equal to 250. Corresponding to 1000 RPM, we already calculated the EB1 as 250. Therefore, we are substituting directly that 250 here. And then from this equation, we are Ia2, I am writing as 0.03 N2, that into Ra plus R external, which is equal to 11, divided by 250, that is equal to N2 by 1000. Therefore, the equation is that, and from this equation, we can reduce that N2 here, 250 N2 equal to 250 N2 equal to 1000 into 280 minus 0.33 N2. Or if you solve this one, N2 equal to the rotor, or the second case, what is the motor speed, which is equal to 482.75, or if you are rounding to the nearest integer, it is equal to 483 rpm. Therefore, when an external resistance of 10 ohm is connected here, the motor speed is reducing to the value 483 rpm. Let us see another problem, 2022 gate question, and that also carry 2 marks. A 4-pole injection motor with inertia 0.1 kilogram meter square drives a constant load torque of 2 Newton meter. The speed of the motor is increased linearly from 1000 to 1500 rpm in 4 seconds. That is, from 1000 rpm to 1500 rpm within 4 seconds. 4 seconds as shown in the figure below. Neglect the losses in the motor. The energy in joules consumed by the motor during the speed change. During the speed change, how much energy is being consumed by the motor? That is the question, and that is to be round off to the nearest integer. As a solution coming here, number of poles here it is given as, number of poles equal to 4. That's 4-pole machine, and inertia is given as 0.1 kilogram meter square, and the load torque is a constant load torque is given, and that is load torque is given as 2 Newton meter, the problem. And the energy consumed by the motor, actually the energy consumed by the motor equal to energy stored in the motor, the rotor, energy stored in the rotor plus energy delivered to the load. Therefore, if you add the energy stored in the rotor with the energy delivered to the load, then you get what is the energy consumed by the motor. Therefore, one by one, let us see that what is the energy stored in the rotor during this transition. That is, energy stored in the rotor during this 4 seconds, during this period, what is the energy stored? That is that we have to find out what is the kinetic energy stored here minus what is the kinetic energy stored at this point. The difference of that one is the energy stored during these 4 seconds. That is given by half j omega m2 square minus half j omega m1 square, where j is the moment of inertia, omega is angular velocity as such. Here, half j omega m2 square. Omega m2 means 1500, and omega m1 is equal to 1000. Substituting this one, half j omega m2 square minus omega m1 square. Of course, here you have to substitute. This is the speed actually. Omega it's a, you have to convert it into corresponding angular velocity as 2 pi n divided by 60. Therefore, it is equal to omega m2 is given by 2 into pi into 1500 divided by 60. 2 pi n divided by 60 whole square minus 2 pi into 1000 divided by 60 whole square. Omega m, this is actually omega m2, and this is the omega m1. Omega m2 square minus omega m1 square, that into the j moment of inertia is given as 0.1 kilogram meter square, and that is half of that one. That will be getting 685.4 joules. That much is the energy stored in the rotor when the speed of the motor changing from 1000 rpm to 1500 rpm. Then that is the energy stored in the rotor. Second is what is the energy delivered to the load. During this period, how much energy is delivered to the load? In order to find out that one, it is equal to the energy delivered to the load is the product of course, the power and time. Or it can say that one integral of P into dt. Or we can say that integral of P equal to T into omega. It is equal to T into omega into dt. Or T is taking outside, T into integral omega dt. That is the energy delivered to the load. T into integral omega dt. Integral omega dt is nothing but the area under this curve. Therefore, T into the area under this curve, that is the energy delivered to the load. Therefore, in order to find out the area, we have to wait. First, we are taking this area, which is equal to this time into this one, or it is equal to what is this area, which is equal to 2 into, that is torque equal to 2 into here. Actually, this one is equal to 4. This is 4 into then this speed is equal to 1000 rpm. Therefore, if you convert it into omega terms, it is equal to 2 pi 1000 divided by 60. Therefore, this is the, we can say the in terms of this is the area here below this one, and this area equal to half bh. It's a triangle. Therefore, half bh means half into 4 into h equal to 500. Therefore, half into 4 into 2 pi into 500, 2 pi n, that is 500 divided by 60. Therefore, if you add this one, that actually we are finding out the area under this curve, and that corresponds to the, of course, the torque into the area under this curve, that is the omega dt, integral omega dt. Therefore, that will be getting, it is equal to 1047.2 joules. Therefore, this is the energy transferred into the or delivered to the load, and this is the energy stored in the rotor. Therefore, the summation of these two will give the total energy input, that is energy consumed by the motor, that is equal to the summation of these two energies, which is equal to 685.4 joules plus 1047.2 joules, which is equal to 1732.6 joules, or if it is rounding to the nearest integer, it is equal to 1733 joules. For that is the answer. Let us see another problem, 2022 gate question, and that also carry 2 marks. A star connected 3-phase 400 volts 50 kVA 50 Hz synchronous motor has a synchronous reactance of 1 ohm per phase with negligible armature resistance. Armature resistance is assuming at 0, and excess or reactance is assumed as 1 ohm per phase. And the shaft load on the motor is 10 kW, while the power factor is 0.8 leading. That is PSH equal to 10 kW and the power factor equal to 0.8 leading. And the magnitude of the per phase excitation EMF of the motor in volts, that is to be round off to the nearest integer. Now, if you see the corresponding phasor diagram, that is here, this is the VA voltage, that is this is the excitation voltage, and the star connected 3-phase voltage, per phase voltage of the input voltage, per phase voltage is, that is actually VA equal to per phase voltage. I am writing a V phase. That is the phasor here. To that one normal case is that IA, here this is the current, armature of the current IA as its synchronous motor current armature or IA. Or here the drop is equal to, actually we have to add IARA. To that one we are perpendicular, you will be adding to IAXS. But since already the armature resistance is negligible, we are neglecting that RA, so that here that IARA drop is neglected, or that is 0. And from this one, the perpendicular to IA, that is this vector, this is perpendicular to IA, and this is corresponding to the drop in the reactance or synchronous reactance JXS into IA. And the vectorial sum of these two will be give the, what we call it as the magnitude of the excitation EMF. That is excitation EMF EA can be calculated as the vectorial sum of VA as well as the drop across the reactance JXS IA. Therefore, that is the way in which can calculate the excitation voltage. Coming back to here, terminal voltage, that is the supply voltage is given as 400 volts, and per phase voltage equal to 400 divided, this vector is equal to 400 divided by root 3, and the rated kVA is given by 50 kVA, and the synchronous reactance is given as 1 ohm per phase, and armature resistance is negligible, RA is assumed to 0, and the shaft power PSH is given as 10 kW, and the load power factor is given as 0.8 leading, or the losses, and here it is the loss in the motor is given as 2 kW. The loss in the motor is given as 2 kW, and the shaft power is given as 10 kW. Therefore, the total input power we have to calculate, which is equal to the shaft, what is the output power available at the shaft, 10 kW plus the losses 2 kW. We will be getting 12 kW is the total input power, and that is equal to, it's a 3-phase case, root 3 VL IL into cos phi. Cos phi is equal to 0.8, and here VL is given as the 440 volts. From that one we can calculate what is the per phase, line current. Line current can be calculated. The line current IA is given by 12 into 10 raised to 3 divided by root 3 400 into 0.8 or 21.65 amperes. That is the line current. Therefore, the input power factor here, the input power factor is given as cos phi equal to 0.8 leading. That is given the problem. Therefore, here you can calculate the EA. EA can be calculated, which is equal to V phase. That is V phase means VA. That V phase cos phi. That is this one. The component of V phase or VA along the current phase. That is V phase EA equal to V phase. V phase cos phi. That is this one, because the drop in IAR is 0. That is why V5 cos phi whole square plus this one. This is equal to V5 sin phi plus this one. This is equal to IA XS whole square. Then we'll be getting what is the excitation EMF. EA can be calculated. Now continuing the same problem, 2022 gate question, same problem here. EA is to be calculated, which is the vectorial sum of course, VA or V phase, and this is one JXS. Therefore, here we are getting the component of VA along IAX, and then that square plus the component of VA, the perpendicular to that, this vector, which is equal to V5 sin phi plus this one plus IAXS whole square. Therefore, that is the EA square, or that is under EA equal to square root of that one. Therefore, EA equal to square root of V phase is given by 400 divided by, here we can see that one, it is equal to 400 volts, which is equal to 400 volts. That is line voltage. Therefore, it is equal to 400 divided by root 3 into power factor is given by 0.8, that whole square, plus 400 divided by root 3 into corresponding sin phi equal to 0.6 plus IA 21.65 into XS is given by 1 ohm per, that is XS 1 ohm per phase. Therefore, that square, and then we will be getting it is equal to 244.54 volts, or approximating to the rounding to the nearest integer, it is equal to 245 volts. Therefore, that is the answer, 245 volts. Now let us see another problem, 2022 gate question that carry 2 marks. A 3-phase 415 volts 4-pole 50 Hz induction motor draws 5 times the rated current at the rated voltage at the starting. When your rated voltage is applied, it takes 5 times the rated current at the starting. It is required to bring down the starting current from the supply to 2 times of 2 times of the rated current using a 3-phase auto transformer. That is, it is the starting current is given to the 2 times the rated current. If the magnetizing impedance of the induction motor and the no load current of the auto transformer is neglected, then the transformation ratio of the auto transformer is given by, that is, round off to the 2 decimal places. That is the question. Now coming to this one, the photos, or of course the reduction diagram is given here. This is a DOL starter, direct online starter. That is directly that is stator is directly connected. Therefore, in 3-phase 4-pole 415 volts 50 Hz induction motor, that is the stator of that one. And in DOL starting method, that is directly online starting method, you know that one. If this is the voltage is equal to, say, this is a V1 voltage, per phase voltage equal to, say, V1 here, and if this impedance, what is called the equivalent standstill impedance per phase, that is please diagram, that is this impedance, the impedance per phase of the stator, per phase standstill impedance of the stator, that is equal to, that is equivalent standstill impedance per phase, that is equal to Z, which is equal to Z01. Therefore, here when direct applying this voltage, say here the voltage equal to, if it is equal to the V1, or the line voltage is equal to root 3 times V1, here if this voltage equal to V1 and this current is given by V1 divided by this impedance, or that is equal to V1 divided by Z01, and that is given as, when a DOL starter is coming, it takes the 5 times the rated current, it times 5, therefore that is equal to 5 times I rated, that is equal to 5 times I rated. I am marking it as a equation 1. Now where we can see that one, it is the equivalent standstill impedance per phase, that is this impedance. Now, and when we are connecting an auto transformer like this one, when an auto transformer, this is a three-phase auto transformer, and this is the, of course, that auto transformer ratio. That ratio of the auto transformer is marked as X here. Therefore, if this voltage is equal to V1 and this is equal to X times V1, X times V1, that is the voltage coming across the stator phase, that is equal to X times V1. Therefore, this current is given by X times V1 divided by Z0 Z010. Therefore, X times V1 divided by Z010 is the stator current. But what the current is reflecting at the input is that since the ratio is X here, because as per the transformer theory, as that ratio of the currents here, this current is given by X times this current, or X times this current means that it is equal to X times whatever this current, that is, the current at this side, secondary side of the auto transformer, that is going to the stator per phase current, is given by X times V1 divided by Z01 is equal to Z010, and that into X, or that is equal to, that is the case, the current at the input here when a auto transformer is connected, and that current is taken as 2 times the rated current, which is equal to 2 times rated current. That is equation 2. Now looking to this one, we can see that V1 by Z01, this is, that is equal to ZD or ZE10, okay, ZD10, that is given as already it is equal to 5 I rated. Substituting that in this equation, we will get it as, but we'll be getting that from these two equations, we'll be getting X square, that is this V1 by ZD10 is given by 5 I rated into 5 I rated equal to 2 I rated, or I rated means rated current, for 2 times rated current. Or from this equation, we can get that X square equal to 2 by 5, or the transformation ratio X equal to square root of 2 by 5 is equal to 0.63. Therefore, this ratio, which is X equal to 0.63, or meaning that the ratio of this one, that this turns divided by this turns, primary side turns over the secondary side, this turn divided by this turn, that is we are taking as X, which is equal to 0.63. Therefore, the answer is 0.63.